All right, so we're going to combine like bits and pieces of two sections into our lesson today. So we're going to look at parts of sections 2, 3, and 2, 5, where today's lesson is going to deal with finding the real zeros of a polynomial function. But before we get into doing that, there are a couple of things we need to look at first. Number one being the remainder theorem. And the remainder theorem says to let f be a polynomial function. And it says if f of x is divided by x minus c, then the remainder is the function's value at c. So c is going to make the value x minus c 0. And again, this remainder theorem only works when we are dividing something of the form x minus c into a polynomial function. All right, so let's do our first example. The directions say to find the remainder if the function f of x, which is 4x cubed minus 3x squared minus 8x plus 4, is divided by x minus 2. Okay, so if we're dividing the polynomial f by x minus 2, we want to take the function's value at the value that makes what we're dividing by equal to 0, which in this case is f of 2. So when we plug 2 into our function, we get 4 times 2 cubed minus 3 times 2 squared minus 8 times 2 plus 4. So 2 cubed is 8 times 4 is 32 minus 2 squared is 4 times 3 is 12 minus 8 times 2 is 16 plus 4. So we get 32 minus 12, which is 20. 20 minus 16 is 4. And 4 plus 4 makes 8. So if we were to divide x minus 2 into that polynomial, f, that would give us a remainder of 8. Okay, let's move on to the next theorem, the factor theorem, which says to let f be a polynomial function, then x minus c is a factor of f of x if and only if f of c is equal to 0. So you should see some similarities with the remainder theorem. And if we were to explain the factor theorem in the context of the remainder theorem, the factor theorem is saying that x minus c is going to be a factor if it gives us a remainder of 0. Because again, with the remainder theorem, if we wanted to find the remainder when we divided x minus c into a polynomial, then we took the function's value at c and whatever number that was equal to gave us the remainder. So if f of c is equal to 0, that tells us that we are going to get a remainder of 0. All right, so a quick example utilizing the factor theorem. The directions here say to use the factor theorem to determine if x minus 2 is a factor of the function f of x, which is equal to 3x to the 4th power minus 6x cubed minus 5x plus 10. So if we want to see if x minus 2 is a factor, we're going to take the function value at the value that makes x minus 2 equal to 0, which is 2. So when we take the function value at 2, that's going to be 3 times 2 to the 4th power minus 6 times 2 cubed minus 5 times 2 plus 10. So 2 to the 4th power is 16 times 3 is 48 minus 2 cubed is 8 times 6, which is also 48, minus 5 times 2, which is 10, plus 10. 48 minus 48 is 0. Negative 10 plus 10 is also 0. So we get that f of 2 is equal to 0, which means that x minus 2 is a factor of the function f. Okay, so next thing we're going to get into is long division. And we're going to long divide polynomials. But before we long divide polynomials, we want to talk about the process of long dividing numbers. Okay, so we're going to go back to like, I don't know, 3rd or 4th grade math, maybe even earlier or later. I'm not sure where it's taught in elementary school, but if we wanted to divide the number 3 into 112, the first thing we do is check to see if 3 goes into the first number 1, which it doesn't. And then we want to see if 3 goes into the number 11 next, which it does. Okay, so we want to determine then how many times 3 goes into 11, which is going to be 3 times. So we're going to write the number 3 over the second 1 in 11. And then what we would do is we take that number 3, multiplied by the number we are dividing by. So 3 times 3 is 9. And then we're going to subtract that number. Okay, so 11 minus 9 gives us a 2. And then we bring down the next number in line, which is also a 2. And next we want to see how many times 3 goes into 22. So 3 goes into 22 7 times. So again, we're just repeating that process. So we take 7 times 3, which is 21. And then we're going to subtract that number, which gives us a 1. Okay, now if you did this in elementary school, I'm sure what your math teacher taught you was to put like a decimal point, and then you're going to start putting like zeros after the decimal point. So you would bring down like the value of 0 and then repeat the process. But there's actually a better way to do that, because when you run out of numbers here, the numeric value that you get is your remainder. And what we do with the remainder to get like the decimal that results from dividing 3 into 112 is we take that remainder 1 and then we divide that by the number that we were dividing by, which in this case is 3. So 37 and 1/3 is going to give us 37.3 repeating if we were to long divide 3 into 112. Okay, so the process that we use for long dividing numbers is going to be the same as the process that we use for long dividing polynomials. Okay, so we're going to take like the first 2 examples we worked. The first one is the one that we did with the remainder theorem, and the second one we did is the one with the factor theorem, and we want to long divide those polynomials. So if we want to divide x minus 2 into our first polynomial, the first thing you have to check with that polynomial, sorry, I'm going to slide this down a little bit so I have room to work. The first thing you want to check with your polynomial is that you are missing no terms. And when we look at our polynomial in the numerator, we have an x cubed term, we have an x squared term, we have an x term, and a constant term. We are not missing any terms there. If we were missing a term, you would want to put 0 as the coefficient placeholder for that term. And the reason we want to do that is that when we long divide, that's going to line up all of our terms whenever we long divide. Okay, so the way we're going to long divide polynomials is we want to think to ourselves, what times x is going to give me the first term in the polynomial? And that's going to be 4x squared. Okay, and just like we did when dividing numbers, we're going to multiply 4x squared times the polynomial x minus 2. So whenever I distribute, we get 4x cubed minus 8x squared, and then we're going to subtract our result. So 4x cubed minus 4x cubed, those cancel. Negative 3x squared minus negative 8x squared is the same thing as negative 3x squared plus 8x squared, which gives us 5x squared. And then we're going to bring down the next term in line, which is negative 8x. And again, we want to think to ourselves, what times x gives me 5x squared? Okay, and that's going to be positive 5x. So we're going to distribute 5x across both terms out front. So 5x times x is 5x squared. 5x times negative 2 is negative 10x. And then we're going to subtract the result. And when we do that, we get the 5x squareds to cancel. Negative 8x minus negative 10x is negative 8x plus 10x, which is 2x. And then we bring down the last term in line, which is plus 4. What times x gives us that first term, 2x? Well, that's going to be positive 2. When I distribute 2 across both of those terms, we get 2x minus 4. And then when we subtract, the number left over is 8, like we said it would be whenever we work this out with the remainder theorem. So what we do is we take that remainder 8 and write it over x minus 2. And because we get a remainder that is not 0, that means that x minus 2 is not a factor of that polynomial. Okay, I want you guys to work out the next one, so pause the video here, and then we'll work it through together. Okay, so when we work out the next one, again, we want to check to see if we are missing any terms, and we are missing a term here. We're missing the x squared term. So what we're going to do is we're going to put a 0 as the coefficient placeholder for that term. Okay. And now we have all terms accounted for, so we can long divide. So what times x gives me 3x to the 4th? Well, that's 3x cubed. When I distribute that across both terms, we get 3x to the 4th minus 6x cubed. When we subtract, we get 0x cubed. We bring down the next term plus 0x squared. And then what times x gives me 0x cubed? Well, it's 0x squared. So when I distribute, we get 0x cubed minus 0x squared. When we subtract, we get 0x squared. We're going to bring down the next term in line, minus 5x. What times x gives me 0x squared? Well, that's 0x. When I distribute, we get 0x cubed minus 0x squared. 0x squared minus 0x. My apologies. And then when we subtract, that gives me negative 5x. We bring down the next term in line, plus 10. And what times x gives me negative 5x? Well, that's negative 5. And when I distribute negative 5 across both terms, we get negative 5x plus 10. We subtract, that gives us a remainder of 0. So that's great. That tells us that x minus 2 is a factor, just like we did when we worked the problem out earlier. So if x minus 2 is one of the factors, then the other factor is going to be 3x cubed minus 5. Okay, now we're going to work through these same two problems using a more efficient technique called synthetic division. Okay, so with synthetic division, again, synthetic division only works when we are dividing a polynomial by something of the form x plus or minus some number. Okay, so if we're going to take the same problem, so again, we're going to take x minus 2 and divide it into this polynomial here, 4x cubed minus 3x squared minus 8x plus 4. Then the way synthetic division works is you're going to take the number that makes what you're dividing by 0, which in this case is 2, and then you're going to list the coefficients of your polynomial. Again, if you have a missing term, you have to put 0 as the coefficient placeholder for that term. Okay, so that's going to be 4, negative 3, negative 8, and 4. And the way synthetic division works is you're going to leave yourself a space, you're going to put a bar, and then you're going to put a box underneath the last value. Okay, so the way synthetic division works is you're going to bring the first number down in line, which is going to be 4. And then you're going to multiply the number out front, 2, times this number 4. And that's going to go underneath the next value. So 2 times 4 gives you 8. Then you're going to add those two numbers. So negative 3 plus 8 gives you 5. Then we multiply 2 times 5, which gives us 10. We add negative 8 and 10, which gives us 2. And then we multiply 2 times 2, which gives us 4. The last numeric value that goes in our box is the remainder. Okay, so again, because we get a remainder of 8, that tells us that x minus 2 is not a factor. But if we wanted to take a look at what we get when we divide x minus 2 into that polynomial, we're going to get x minus 2 times these values that we get here are going to be coefficients for our remaining function. So because we're dividing x into 4x cubed, the first number is going to be the coefficient of, in this case, the x squared term. Okay, so that's going to be 4x squared. The next value, 5, is going to be the coefficient for the x term. The next value, 2, is the constant. And then the number in the box, 8, is going to be our remainder. And that's exactly what we came up with up above here, whenever we did long division. It's just synthetic division is a much more efficient way of dividing a linear term into a polynomial function. Okay, let's do the same thing for the next example. All right, so again, with the second example we looked at, we were dividing x minus 2 into 3x to the fourth minus 6x cubed plus 0x squared minus 5x plus 10. So again, the value that makes that factor 0 is 2. And then we're going to list the coefficients. So again, our coefficients are 3, negative 6, 0, negative 5, and 10. We leave ourselves a line of space, and then we're going to put a box underneath our final value, which is going to be our remainder. Okay, so again, we bring down the first term in line 3. 2 times 3 gives us 6. That adds up to 0. 2 times 0 gives us 0. That adds up to 0. 2 times 0 gives us 0. That adds to negative 5. 2 times negative 5 gives us negative 10. And that adds to 0. Okay, so because we get a remainder of 0, x minus 2 is a factor. And then if we want to see the polynomial that results whenever we factor that out, if we're dividing x into 3x to the fourth power, then that first coefficient here is going to be the coefficient of our x cubed term, which is going to be 3x cubed. The next term, the next number is going to be the coefficient of the x squared term, which is 0x squared. I don't have to write that. The next number is the coefficient of the x term, 0x. I don't have to write that either. And then the last term is the constant term, which is minus 5. And that's exactly what we came up with up above. The x minus 2 is a factor. When we factored that out, that left us with 3x cubed minus 5. Okay, so synthetic division is going to be super important with what we're doing later on in today's lesson. Okay, the next thing we're going to look at is Descartes' rule of signs. So Descartes' rule of signs says to let f denote a polynomial function written in standard form. And then it's 2 parts. So number 1 says the number of positive real zeros of f either equals the number of variations in the signs of the non-zero coefficients of f of x, or else equals that number less an even integer. It sounds super complicated. If you guys can count to like 5, it's really easy to do. Okay. And then the second part says the number of negative real zeros of f either equals the number of variations in the signs of the non-zero coefficients of f of negative x, or else equals that number less an even integer. Okay, so we're going to do two examples really quick with Descartes' rule of signs. So the directions say to use Descartes' rule of signs to determine the number of positive and negative real zeros the function may have. And for number one, we have the function f of x equal to negative 4x to the 7th plus x cubed minus x squared plus 2. Okay, so if we want to get the number of positive zeros, positive real zeros the function may have, what we want to do is we want to count the sign variations in the coefficients of f of x. So if we look at the function f of x, it starts negative. The next term changes to positive, so that's one sign variation. The next term changes to negative, that's two sign variations. The next term changes to positive, that's three sign variations, okay? Which means that there are three, or that number less an even integer. Okay, so the smallest even integer that we can subtract from 3 is 2. So 3 minus 2 is 1. So there are 3 or 1 positive real zeros. If you had a polynomial function that had like 7 sign variations of f, that means there would be 7 or 5 or 3 or 1 positive real zeros. If it had like 4 sign variations, there would be 4 or 2 or 0 positive real zeros. Okay, if we want to get the number of negative zeros, we want to count the sign variations of f of negative x. So I'm not going to show the step of actually plugging negative x in the place of x. What I do need to know is that if the exponent of x is odd, that's going to change the sign of that term. And if the exponent of x is even, that's going to keep the sign of that term the same. So when we take f of negative x for this function, that's going to give me 4x to the 7th minus x cubed minus x squared plus 2. And then we want to count sign variations of f of negative x to get the potential number of negative real zeros. So when we count sign variations, the first term is positive. The next term changes to negative, so that's one sign variation. The next term stays negative, that's still one sign variation. The last term changes to positive, so that's two sign variations, meaning there are 2 or that number less an even integer. So 2 minus 2 is 0. So there are 2 or 0 negative real zeros. Okay, when we do 2, so for number 2, we want to count, if we want to determine the potential number of positive zeros, we want to count the sign variations of f of x. So the first term in f of x is positive. The next term is also positive, so there's no sign variation there. The next term changes to negative, so there is one sign variation, meaning that there is one positive real zero. Okay, to get the number of potential negative real zeros, we want to count the sign variations of f of negative x. So f of negative x, again, the terms of even degree keep the same sign. The terms of odd degree change sign. So f of negative x is going to become x to the 4th minus 5x cubed minus 2. Again, the first term is positive. The second term changes to negative, so that's one sign variation. The next term stays negative, so that's still one sign variation. So there's going to be one negative real zero. Okay, so again, the terminology sounds really complicated. It's just a matter of counting to determine the positive and negative real zeros. Okay, last component for us to look at before we actually start getting into some real examples. So that is the rational zeros theorem, which states to let f be a polynomial function of degree 1 or higher of the form f of x is equal to, and then I'm just writing like the general form of a polynomial function. So how polynomial functions are defined in math. Okay, so that's going to be the function f of x equal to a sub n times x to the n power plus a sub n minus 1 times x raised to the n minus 1 power plus all the way out to a sub 1 times x plus a sub 0, where a sub n cannot be equal to 0, a sub 0 cannot be equal to 0, and lastly, and this is important, where each coefficient is an integer. Okay, so if your coefficients are not integers, then you have to factor a number out of your polynomial in order to make those coefficients integers. Okay, so if like one of your terms has like a coefficient of 1/2, then you have to factor 1/2 out of your polynomial in order to make all of the coefficients integers. Okay, so the rational zeros theorem states that if P over Q in lowest terms is a rational zero of f, then P must be a factor of a sub 0. So P has to be a factor of the constant term a sub 0, and Q must be a factor of the leading coefficient a sub n. All right, so let's do a quick example utilizing the rational zeros theorem. So it says to list the potential rational zeros of the function f of x, which is equal to 2x to the 5th power minus x cubed plus 2x squared plus 12. Okay, so first thing we check is that all the coefficients are integers, so that checks out. Okay, so our p-values are going to be factors of the constant term. So if we think about the factors of 12, if I list the factors of 12 from smallest to largest, the smallest factors of 12 are plus or minus 1, then plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And then our Q values are factors of the leading coefficient. So the leading coefficient here is 2. The factors of 2 are plus or minus 1 and plus or minus 2. So we want to get all combinations of P over Q. Okay, so to get the first set, we're going to take all of those p-values and divide them by 1, which are just going to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. And then next, we want to take all of those p-values and divide them by the q value of 2. So 1 divided by 2 is going to give us plus or minus 1/2. 2 divided by 2, we already have that listed as 1. 3 divided by 2 gives us plus or minus 3/2. 4 divided by 2, we already have that listed as 2. 6 divided by 2, we already have that listed as 3. And 12 divided by 2, we already have that listed as 6. Okay, so what the rational zeros theorem says is that if your graph has like a rational zero, So if it has an x-intercept that is going to occur at a rational number, it has to occur at one of those p over q values. Now, this is not a good scenario for you guys. This is a lot of values, like a lot of potential rational zero values for you to test. I mean, I guess it could be worse. Like you could have your p-value be like the number 24, or even worse if you had it like the number 72. Like 72 has so many factors, okay? But to have this many p over q values, 2, 4, 6, 8, 10, 12, 14, 16, like that's a lot of values for you to test. And you guys are going to see as like we work through these problems, if you're really lucky when it comes to testing p over q values, your homework assignment's going to go really fast. If you're unlucky, you better have a good eraser handy because you're going to have to test a lot of p over q values to see which ones work. Okay, now when it comes to you guys taking a test, like I'm going to try to pick polynomial functions where it limits the number of p over q values for you guys to test, because I don't want it to be like on a test where it's all about luck, you picking the right p over q value. I want it to be where you understand the process properly and can work things through. You guys are going to see when I work these problems out, like I'm supremely lucky. I pick the right p over q value every time. I'm just kidding. I'm not that lucky, but the fact of the matter is I've worked these problems out, so I know what p over q values work. Okay, but you guys aren't going to have that luxury, so hopefully you're lucky when it comes to picking values for your homework. Okay, so let's get into some actual examples with this. So the directions for the first one ask you to find the real zeros of the function f of x, which is equal to 2x cubed plus x squared plus 2x plus 1. Okay, first thing you always want to try when finding real zeros is check and see if you can factor your polynomial, which in this case, we can factor our polynomial by grouping. If you can factor using standard factoring techniques, it makes the problem easier for you guys to work through. Okay, so always check to see if you can factor using standard factoring techniques first. Okay, so I'm going to factor this by grouping. So when I look at the first two terms, the greatest common factor of the first two terms is going to be x squared. So when I factor that out, that leaves me with 2x plus 1. And then I can factor a positive 1 out of the next two terms, which also leaves me with 2x plus 1. So 2x plus 1 is my common factor. I'm going to pull that out. And when I factor that out, that leaves me with x squared plus 1. We know x squared plus 1, that does not have any real zeros. So the only real zero here occurs where 2x plus 1 is equal to 0. And that happens when x is equal to negative 1/2. Now, when we look at the multiplicity of that 0, the multiplicity of that 0 is 1. So we know our graph is going to cross the x-axis at that point. Okay, so that's it. That's all we have to do for this is find the real zero only. And again, if you can factor, factoring is, like standard factoring is the most efficient way for you to work through a problem of this type. Okay, but let's say you goofed up and didn't realize that you could factor this by grouping, okay? Or you have a polynomial that you can't factor using standard factoring techniques. We're going to take what we talked about today with Descartes' rule of signs and the rational zeros theorem and use that to help us find zeros as well. Okay, so when I use the when I use Descartes' rule of signs here, if I want to count the number of sign variations, the first term is positive, the next term stays positive, the next term is positive, the last term is positive. So there are 0 positive real zeros because there are 0 sign variations for f of x, which that's really good news for us. And we'll take a look at why in a second. Okay, If we want to get the number of negative zeros, we're going to count sign variations of f of negative x. So f of negative x becomes negative 2x cubed plus x squared minus 2x plus 1. And when we count sign variations here, the first term is negative. The next term changes to positive, so that's 1. The next term changes to negative, that's 2 sign variations. The last term is positive, that's 3 sign variations, so there are 3 or 1 negative real zeros. Okay, next we want to get our p over q values. So our p values are factors of the constant term, which are just plus or minus 1. And the q values are the factors of the leading coefficient, which are plus or minus 1 and plus or minus 2. So all combinations of p over q are just going to be plus or minus 1 and plus or minus 1/2. So we have a way better situation here. We only have 4 potential p over q values, but the fact that we use Descartes' rule of signs to show that there are 0 positive real zeros, we only have to test the negative 0. So we only really have 2 values that we have to test, okay? So I have a good feeling about negative 1/2. We're going to test that. So I'm going to do synthetic division with this. Again, I'm not missing any terms in this polynomial. So we have the coefficient of the x cubed term is 2. The coefficient of the x term is 1. The x squared term is 1, the coefficient of the x term is 2, and the constant term is 1. And then we're going to put a box underneath that last value to house the remainder. Okay, so we bring down the first number in line 2, and then we multiply negative 1/2 times 2, which gives us negative 1. That adds to 0, multiplies to give us 0, adds to give us 2, multiplies to give us negative 1, adds to give us 0. So great, we picked the right value because that gave us a remainder of 0. So if negative 1/2 is a 0, then x minus negative 1/2, which is the same thing as x plus 1/2, is going to be a factor. And when we factor that out, this right here gives us the coefficients of our remaining polynomial, okay, which is going to be 2x squared plus 2, which doesn't quite look like the factored form that we had factoring by grouping, but I'm going to do a little bit of algebra to this real quick. So when I look at this second polynomial here, that has a factor of 2 that I'm going to pull out front. And then I'm going to take 2 and distribute it across this polynomial here, which gives me 2x plus 1 times x squared plus 1, which is the exact same factored form that we got before. And again, our only 0 here is x is equal to negative 1/2. Again, not nearly as efficient as factoring by grouping would be for this particular polynomial. Okay, but again, we're not going to be able to factor all polynomials using standard factoring techniques, and we'll see that with the next example that we look at. So the directions here ask us to factor. So again, the directions are different. We're not asked to find the real zeros. We're asked to factor this polynomial. So we want our final answer in factored form. Okay, so we have the polynomial f of x equal to x cubed plus 4x squared minus 25x minus 28. And when we look here, like there's no way we can factor this by grouping, because I can't, like what I factor out of the first 2 terms, x squared, that leaves me with x plus 4. There's nothing I can factor out of the last 2 terms, which is going to leave x plus 4 in the parentheses. Okay, so factoring by grouping, not going to work for me here, which means I have to use Descartes' rule of signs and the rational zeros theorem and like synthetic division to test here. Okay, so using Descartes' rule of signs, when I count the sign variations, f of x starts positive, the next term is positive, the next term changes to negative, that's 1 sign variation, the next term stays negative. So that means that there is one sign variation, meaning that there is one positive real zero. Okay, to get the number of negative zeros, we want to count sign variations of f of negative x. So when we take f of negative x, that's going to become negative x cubed plus 4x squared plus 25x minus 28. So when we count sign variations here, the first term is negative. The next term changes to positive. That's one sign variation. The next term stays positive, so that's still 1. The next term changes to negative, so that's 2, which means that there are 2 or 0 negative real zeros. Okay, next, we want to get our potential rational zeros, so our p over q values. So our p values are going to be factors of the constant term, which when I go from smallest to largest, that's going to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 7, plus or minus 14, and plus or minus 28. Our q value is the factor of our leading coefficient, which are just plus or minus 1. So our p over q values are just plus or minus 1, 2, 4, 7, 14, and 28. Okay, so I'm going to use Descartes' rule of signs. I know there has to be one positive real zero. And I don't know about you, but like positive 4 is just speaking to me saying pick me. So we're going to pick positive 4. I got a good feeling about positive 4. Hopefully you guys are number whisperers like me, and they speak to you as well. So when we do synthetic division with number 4, we're going to list the coefficients of our polynomial. So I'm not missing any terms. So the first coefficient is 1. The coefficient of the x squared term is 4. The coefficient of the x term is negative 25. And the constant term is negative 28. And then we're going to do synthetic division here. So we bring down the first term in line 1. 4 times 1 is 4. 4 plus 4 adds up to 8. 4 times 8 is 32. Negative 25 plus 32 is 7. 4 times 7 is 28. Wow. Thank you, number 4, for calling my name. So that means we get a remainder of 0. So x minus 4. So 4 has to be a 0. X minus that number. X minus 4 has to be a factor. And when we factor that out, that leaves us with x squared plus 8x plus 7. And when we look at x squared plus 8x plus 7, that's factorable. So that's going to factor to x plus 1 times x plus 7. Okay, so again, that's the factored form. If the problem asks us to find the zeros would be x is equal to 4, x is equal to negative 1, and x is equal to negative 7. So again, that has the one positive real zero like it was supposed to, and the 2 negative real zeros. And if you guys wanted, you could sketch the graph of that. The graph, because the multiplicity of all of those zeros is odd, the graph is going to cross the x-axis at all of those points. You could determine the end behavior being x cubed. You could get the y-intercept to be negative 28, and then you could use that stuff to sketch the graph of that function, which we'll do a graph after this next example. Okay, so directions here say to solve the equation in the real number system. I want you guys to give this one a try. Again, this is not factorable by grouping. Okay, so you have to use Descartes' rule of signs and the rational zeros theorem here. Okay, so with this one, we're counting sign variations for f, so there is only 1, which means there's one positive real zero. When we do sign variations for f of negative x, that's going to become negative 2x cubed minus 3x squared plus 3x minus 5, which means when I count sign variations there are 2, which means that there are 2 or 0 negative real zeros. Okay, so our p-values are factors of the constant term, which are just plus or minus 1 and plus or minus 5. Q-values are factors of the leading coefficient, which are plus or minus 1 and plus or minus 2. So our p over q values are plus or minus 1, plus or minus 5, plus or minus 1/2, and plus or minus 5/2. Because there's one positive 0, I know I'm going to test the positive values first, and I got a good feeling about 5/2. So again, we check our polynomial f. Are we missing any terms? And the answer is no. So we're just going to list the coefficient placeholders, like coefficients for those terms, which are 2, -3, -3, and -5. Leave ourselves a space, and then we're going to put a box underneath the last value to house the remainder. And then we bring down the first number in line 2. 2 times 5/2 is 5. That adds up to 2. 2 times 5/2 is 5. That adds up to 2. 2 times 5/2 is 5. And that adds up to 0. Which is great. We picked the right value. And if you didn't, don't worry about it. You just go on and test a different value. Okay? And realistically, like, that's going to happen with everybody. So the bottom line is you want to be really quick and accurate with synthetic division, because the faster you can go through that, the faster you can test values to see which ones work and which ones don't. Okay, so that means that 5/2 is a 0. So x minus that number, x minus 5/2 is going to be a factor. And then when we factor that out, that leaves us with 2x squared plus 2x plus 2. And then what I'm going to do is I'm going to factor a 2 out of that trinomial. And then I'm going to distribute the 2 into the binomial out front. So that's going to give me 2x minus 5 times x squared plus x plus 1. Okay, so we know for sure that x is equal to 5/2. That's a 0 in the real number system. Now, we want to check and see if this quadratic is going to have any zeros. So it's not factorable. So if it's not factorable, that means we either have to use completing the square or the quadratic formula. So I'm going to use the quadratic formula. So x is going to be equal to negative b, which is -1, plus or minus the square root of b squared, which is 1, minus 4 times a, which is 1, times c, which is 1. And we see that our discriminant here is negative. And if our discriminant is negative, that's not going to have any zeros. So the only zeros our polynomial has is x is equal to 5/2. Okay, let's move on to the next example. So the directions for the next one say to factor and graph the function f of x is equal to x to the 4th minus x cubed minus 6x squared plus 4x plus 8. Okay, I want you to try factoring this first. So pause the video, factor. Whenever you're done, turn it back on. I'll work it through. And then if you want to pause before I graph, that's fine. And then you can check your graph against mine. Okay. So when we look at this polynomial function has 5 terms. Typically, you can't factor that by grouping, although you can factor this by grouping. It's really tricky and really creative. I'm not going to show you how to do it, but it is potentially possible to factor this by grouping as well. Okay, so I'm going to use Descartes' rule of signs and the rational zeros theorem. So when I count sign variations of f of x, there are 2 of them, which means that there are 2 or 0 positive real zeros. And then when we do sign variations of f of negative x, f of negative x is going to become x to the 4th plus x cubed minus 6x squared minus 4x plus 8. And when we count sign variations there, we also have 2. So there are 2 or 0 negative real zeros. So to be honest, like Descartes' rule of signs really didn't help us here. Okay, so next we want to test the p over q values. And since q, the leading coefficient, is 1, like the p values are going to give me the p over q values. Okay, which are going to be the factors of 8, which are plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. Okay, so I'm going to pick the 0 of negative 2, and I'm going to do that for a specific reason. And I'll explain why in a second. Okay, so we're going to do synthetic division with negative 2. Again, when I look at my function f, I have coefficients for all the terms. X to the 4th, x cubed, x squared, x, and constant. So we're going to list those coefficients. So we have 1, negative 1, negative 6, 4, and 8. And then we're going to do synthetic division here. So we bring down the first term 1. Negative 2 times 1 multiplies to negative 2, that adds to negative 3, multiplies to 6, adds to 0, multiplies to 0, adds to 4, multiplies to negative 8, and adds to 0. So that's great. We found our first 0. Okay, so if negative 2 is a 0, x minus that number, so x minus negative 2, which is x plus 2, is going to be a factor. And when we factor that out, that's going to leave me with x cubed minus 3x squared plus 4. Okay, so the reason that I picked negative 2 is if you guys picked any other 0 that works, I actually think when you get to this step here, you're going to get a polynomial that you can factor by grouping. And if you get a polynomial that you can factor by grouping, factor it by grouping. Like once you get to a point in this problem where you can factor using standard factoring techniques, we want to do that. Okay. The reason I picked negative 2 is that we don't get a polynomial that we can factor using standard factoring techniques. Okay. Now the good news for us here is that like once we get to this point, we don't have to do like Descartes' rule of signs or the rational zeros theorem again. So whatever applied to the original polynomial also applies to this polynomial. So what we want to do is we want to take the polynomial that we have in that's highlighted, and I want to do synthetic division on that so I can further break that polynomial down. Okay, so I know for sure that there is one negative real zero. So Descartes' rule of signs tells me that there has to be a second negative real zero. Okay, and the one I think that's going to work for us is negative 1. So let's do synthetic division with that really quick. So again, I'm missing the x term, so I'm going to write 0 as the coefficient placeholder for that term. So our coefficients are 1, negative 3, 0, and 4. And then we're going to perform synthetic division. So we bring down the first term 1, multiplies to give negative 1, adds to give negative 4, multiplies to give 4, adds to give 4, multiplies to give negative 4, and adds to give 0. So we already have that x plus 2 as a factor. We know that negative 1 is a 0, which means that x minus that number. So x minus -1 is x plus 1. That is a factor as well. And the resulting polynomial that we get is x squared minus 4x plus 4. And x squared minus 4x plus 4 factors to x minus 2 quantity squared. Okay, so that is our polynomial factored completely. Okay, now, one thing I want to mention to you guys, if you tried testing +2, so if you did like synthetic division with +2 and found that to be a 0, you know that Descartes' rule of signs says that there has to be a second positive 0. So if you tried testing all of the other values, all the other positive values like 1, 4, and 8, and none of those worked, it could be possible that you have to use 2 a second time, which that is the case here because x minus 2 has a multiplicity of 2, which means that that root works as a solution twice. Okay, so it could be where a 0 works more than once, and if that's the case, then it's going to have a multiplicity that is not 1. Okay, so if we wanted to do a quick sketch of the graph here, we know the x-intercepts based on these factors are going to be the ordered pair -2, 0. Because the multiplicity of that is 1, the graph is going to cross. We know it has another x-intercept at -1, 0. Because the multiplicity of that is 1, the graph is going to cross. And it also has an x-intercept at 2, 0. Because the multiplicity of that is even, that means the graph is going to touch. We know the y-intercept is going to be the ordered pair 0, 8. And lastly, we know the end behavior of y is equal to x to the 4th is going to look like that. Okay, so once I know all those things, I can do a quick sketch of the graph of my function. Sorry. Okay, so we have x-intercepts at -2, 0. We have one at -1, 0. We have a y-intercept at 0, 8. And we have our last x-intercept at 2, 0. We know the end behavior of our function looks like this and like this. We know our graph is going to cross the x-axis at -2. Crosses the x-axis at -1. And then it touches the x-axis at 2. So again, that's just a very rough sketch of the graph of that function. But that's tying this lesson in with the lesson that we looked at in class last week. Okay. So last thing for us to go over is the intermediate value theorem for continuous functions. And that says that if f is continuous on the closed interval from a to b, so because we're looking at polynomial functions, we said that polynomial functions are continuous functions everywhere. So they have to be continuous on the closed interval from a to b. Then f of x has to take on every function value. So that means that it has to hit every y value in between f of a and f of b. Okay. So if the function is continuous, when I plot those 2 points at a comma f of a and b comma f of b, let me erase this really quick. Okay, when I plot those 2 points, if that function is continuous, that means I have to be able to connect those 2 points without lifting my writing utensil. Which means that all of the y values have to be hit in between those 2 numbers. Okay, so every y value between f of a and f of b have to be covered up by that graph. Okay, so let's do a quick example illustrating the intermediate value theorem for continuous functions. So the directions here say to explain why the function f of x, which is equal to x squared minus 1, must have an x-intercept on the closed interval from 0 to 2. Okay, so again, explain why that function must have an x-intercept on the closed interval from 0 to 2. Okay, so our explanation, number one, is that f of x, which is equal to x squared minus 1, is continuous on the closed interval from 0 to 2. Okay, again, f of x is a polynomial function. It's a quadratic function. It's continuous everywhere. Okay, what we want to do next is we want to test f's value at the two endpoints. Okay, f of 0 and f of 2. So when we test f's value at 0, when I plug 0 into that function, we get an output of -1. And when I plug 2 into the function, 2 squared is 4 minus 1 is going to be 3. Okay, so let me just write up the explanation really quick. So f of x, so since f of x, which is equal to x squared minus 1, is continuous on the closed interval from 0 to 2, comma, f of 0 is equal to -1, and f of 2 is equal to 3, the intermediate value theorem guarantees some point C on the open interval from 0 to 2 where f of c is equal to 0. So again, like if you looked at this graphically, like the function x squared minus 1 is going to look like this. It's the graph of x squared just shifted down 1 unit. If you looked at that on the closed interval from 0 to 2, so graphically the function looks like so. If the function is continuous, that means it has to hit every single y value in between -1 and the y value here, which is 3. So it has to be equal to 0 at some point because it hits every single y value in between -1 and 3. Okay, so again, that's just a quick example with the intermediate value theorem. All right, guys, so that wraps up this lesson. Make sure you're on the lookout for your homework assignment. I just combined this into one long video. I was tired of like uploading 3 different videos for all 3 of my classes, so I'm just going to do one big video. It's just going to make it easier for me in the long run. Okay, so hope you guys are having a great week, and we'll see you in class on Monday. Take care.